Okay, hello everyone. Welcome to our 8th Geometry Topology Summer School, Research Summer School. Our first speaker is Eyüp Yalçınkaya from University of Rochester, and he's going to talk about lectures on spin 7 geometry.
Hello everybody, thank you for coming to the summer school, and also I would like to thank the organizing committee for this summer school. And this new lecture series I will talk about spin 7 geometry, and this geometry is famous for the relation between lots of parts of the geometry, and especially string theory and kinds of modern physical objects. And first two or maybe three lectures, introductory materials, and if you know, you can listen roughly. At the end of the lecture, I will continue with the mirror duality and some relation with the spin 7 geometry. Okay, we can continue. I will write on the Jamboard 2 or 3 days, and at the end of the lecture, I will continue with the, this PDF screen. And actually, the spin 7 geometry is resembles like a little bit the Kähler geometry. So what's the meaning of a Kähler geometry? It's more or less a generalization of complex geometry with some spatial information. And our lecture contains spin 7 geometry. Some introductory material, and especially related to holonomy. And somehow we have to measure something. We need metric, and we need some angle preserving. These kinds of information we need round algebra, and the spin 7 geometry is a 8-dimensional object, and that's why we need octanium. And then spin 7 structure and manifolds. And maybe we can call it the Calabi-Yau manifolds. Mirror duality, and mirror duality on spin 7 manifolds. Here, this is the general coach want to talk. Actually, at the beginning, the vector calculus is enough for non-relativistic geometry or non-relativistic physics. After that, after the relativity, we need some tensor calculus, because the starting point change and the behavior of the physics defined after tensors, after relativity, and after quantum mechanics, and we need a Spinorian calculus. to be able to combine the relativity and the quantum mechanics. That's the famous idea, 10-dimensional or the 11-dimensional object combine the relativistic quantum theory So for this theory, actually we have 4-dimensional object and 6-dimensional Calabi-Yau manifold, or for this theory we have the 10-dimensional object, or in some theory things that we can think about the 11-dimensional object, and the boundary is the 10-dimensional object. So all of them more or less induced from the same theory, but the different part of the theories. And that's why, I mean, for this theory, we have to understand the Calabi-Yau manifolds. These Calabi-Yau manifolds in hidden dimension. Okay. For this theory is related with the relativity theory, and the spinorial calculus needed 10-dimensional and also the 11-dimensional object. And to be able to understand this theory, we need, as I mentioned, the holonomial, normed algebra, octanion, and system 7 calculus, and the Calabi-Yau manifold, and the mirror duality is famous for the physical correspondence, and that's why we have to understand. And can we find our questions? Can we find the correspondence of the mirror duality on system 7 manifold? Because the mirror duality in general related with the Calabi-Yau manifolds, and the Calabi-Yau manifolds. Calabi-Yau manifolds related with 6-dimensional objects, so we try to find the correspondence between the spin 7 manifolds and the Calabi-Yau manifolds. Okay, we can start with the holonomy. If we have the Riemannian manifolds and metric connected Riemannian manifolds, so if we have gamma on this space such that this is a loop at x in M, okay, so as you think, I mean, if you define something, you have to improve, you have to go forward a little bit. Defining it is not enough for us. We have to again define the tangent space of M at this point, and for this loop we are looking at the tangent space. How does the tangent space, or how does the, this vector in this tangent space under this loop here, the P alpha named by the parallel translation, of V around gamma. Okay. So here the non-standard picture actually. Maybe we can guess the background of attendance. So we can start from the plane. So if you define this is, let's say, M, the standard 2-dimensional plane, if you start with an object here, the loop gamma, and your vector at this point like this turning around, and you are living in a 2-dimensional object, and the same points, okay, you can find the same tangent vector. But if you distort your geometry, your MN, the non-standard object, the sphere. So now we are living on a surface of a sphere, and for this sphere, we can define the loop like this. This is our loop. And for this loop, if you start with the vector from somewhere, and the vector you can slide on this loop, okay, at this point. The parallel translation means you have to preserve the angle between the differential and that vector. I mean, the differential here, if you look at that, you have to preserve the angle. That's why this curve turned, and your now the vector has to be turned also. At this part, your tangent is like this. Okay, so your angle has to preserve, and you have to continue like this. Okay? This is the name of the parallel translation. You have to preserve the angle. If you do a tangent, so we start with this vector, okay? But at the end of the loop, our final vector is a little bit different than the starting vector. I mean, if you compare that flat surface, starting and the ending vector are the same, but if you look at the sphere, because of actually the curvature, because of the bending, your final vector is a little bit different, and this difference can be measurable. Okay, so how can we measure? Here we can define the holonomy group. This is named by the holonomy. Actually, holonomy group measure of this changing. Okay, here, if you think about that, there's no change, so the holonomy group is actually trivial. But for looking at the sphere, we can see the different result for holonomy group. So how do we define the holonomy group? Is this one. Mg at x in M, and it's nothing but the whole G with respect to x. So we only defined everything with the special point, and the element of P gamma tangent space to tangent space. This is nothing but, I mean, this change can be defined as the element of the GLM, right? Because everything occurs in the tangent space. So Tx n and gamma group at okay, we can say that the elements of the GLTXN, the rotation of all rotation at the x as a define a group, because this why it's group, because we have, I mean, this group is just can be seen as a group element, but the inverse also has the element of the same group, right? P alpha. If you reverse the direction, you can find the P minus alpha. So P gamma, P minus gamma, all of them the elements of the same holonomy group at that point, and you can concatenate to the group. You can add them up, and then this summation also has to be elements of the same holonomy group, because the same points, and you can use the combination of the group element. We will find again the new element at that holonomy. So we can say that the holonomy defines a group. Actually, the reduced holonomy group is this one. If you choose a special, group as a special property, actually, the reduced holonomy group of MG at X in M. So the reduced holonomy written as the whole 0 G with respect to X and the P gamma G as Tx and so these kinds of gamma is the real homotopic loop. Trivially, you can feel that this reduced holonomy group somehow the subgroup of holonomy group, but we will see later and we will explain. And the reduced holonomy gives some information, and the holonomy group gives us another information. As I said, the group information is this one. Group structure is via loop concatenation just like for Taiwan X. So for each element of holonomy group can be written as P alpha beta, and for each element as an inverse P alpha bar. Okay. Is there a problem? Can you hear me, Mustafa?
Yeah, we can hear, but a little bit louder is better. Also,
Okay.
adjust the camera, please.
Okay.
Yeah, you're not in the middle of the.
I mean, so I can
It's
change
like
the...
I am talking rather than you.
I have...
Yeah, this is better. Yeah.
Okay, we have two different equipment.
Yeah.
One of them is writing parts, one of them is seeing parts, one of them is hearing parts. Okay. Now our group structure is satisfy the combination and the inverse elements, and also the identity elements is if you choose the point as a loop, you can find an identity element. So directly we can say that the holonomy defines a group, and for again, if you return a simple element, the sphere, we can write here the over again. As I said, if you choose this loop, you will start this tangent somewhere. Okay, it's turn. We find another vector at this tangent plane, and for arbitrary the different group, you will find a different angle. Okay, so all possible angles start with for each loop start with. We will measure our holonomy with this theta of as this theta is one-to-one correspondence between the cosine theta, sine theta, okay, this rotation, and for this for all possible elements is in between 0 to 2 pi actually, and the element is nothing but SO2, and this is S1, and also this is nothing but S1 actually, and we can say that the holonomy of S2 is just S1 or SO2. Okay, standard example for our the non-standard example, as I said, if you have a flat surface, your holonomy will turn out to be directly the identity element, identity group. But if you look at the sphere, you will find them property of the holonomy group. We have to understand this holonomy group and the relation between the curvature relation between the underground geometry, and then we will understand better system geometry. So we know that the parallel translation properties. Parallel translation is isometry. So at the beginning, I said you have to measure the angle between the derivative and the arbitrary vector, and also you have to, if angle is fixed and the length is fixed, you can the isometric preserve that angle and the length of the vector. So for this property, if parallel translation is isometry, we can say that the holonomy somehow has the element of, oh sorry, the subgroup of which group? Actually, we can guess. Sorry. Something missing. I can write and try. Something I can. So, if it is isometry, it preserves angle, it preserves length, and in general, we started that holonomy G is a subgroup of the GL, but we can shrink our group is the OTXM, okay? And because OTXM preserve angle and also of length, if you again reduce holonomy, you will find that orientation preserved. So we can say that Tx. Yeah, okay. So this is our first two property. We can guarantee that holonomy is a subgroup of the orthogonal group because of the isometric property, and reduced holonomy is preserved orientation. But we defined that X is a specific point, but how about another point different than X? So the idea from here, if you start with this point and or any other point somewhere here, so for X and Y is different than each other, we can define the holonomy at X, we can define holonomy at Y, but we know that somehow they are interrelated to each other, and this relation is actually again the tangent plane of M, and somehow we can write that the base point is point independence. Base point independence. How? I mean, the canonical way, somehow we will define another map, another curve from X to Y, like this. So you can shift your idea at the beginning of X to Y directly. And the important part that somehow you have to define the gamma. Let's gamma at from X to Y, then holonomy of G with respect to Y now at the new point, we can write that a P gamma composition of P gamma with holonomy of G with respect to X and P inverse gamma. You can define the holonomy of Y. At first you will start with X, okay, and shift or slide your holonomy to Y, okay, and you will find the holonomy of so if you try to define the holonomy of Y, at first go to X, okay, with this map, and define the holonomy at X and return back. So more or less, I mean, you define holonomy at some point, and you can slide that holonomy around the complete space. And there's no big difference because for the completely, we have to define holonomy for all possible, if you look at that, for all different angle, for all different loop, and actually some loop passing from Y, and so you have to thought before them defining the holonomy at Y. That's why there's no big problem. Just this is the canonical explanation, and for the holonomy is base independent. You can define it everywhere. At first, you have to pick a point. Okay? So, properties. The holonomy 0 means the reduced holonomy is connected. Okay, because we choose always the non-homotopic elements, and these elements defines as connected spaces, and the holonomy, reduced holonomy, is the normal subgroup of the holonomy G. Okay. So if M is simply connected, so we can say that your reduced holonomy is exactly the same as our the holonomy group, because for each point interrelated to each other, and if this simply connected, you can shrink all different holonomy pieces into one holonomy group directly. Okay? And also holonomy 0G is the identity component of G, and also by which reduced holonomy is closed Lie group of SOM, and as a result of this, we can say that the holonomy, the reduced holonomy, is a compact connected Lie group. Okay? So, and generally, for the reduced holonomy group, we can pass the curvature idea, because we know that the Lie algebra of the SOM is the special group, and we know that the holonomy is actually the subgroup of SOM, so the algebra of holonomy here is also the algebra of SOM. And from here, somehow we will relate our holonomy to our curvature. Okay. And we know that the holonomy, again, the holonomy means reduced holonomy at point X is the element of SOTXN. Okay. Orientable group is compact connected Lie group. Okay. So we can define the Lie algebra, call it Lie algebra. We can write like this. The whole G with respect to X is the Lie algebra of So, and we will see, or you can check from the different resources, but the holonomy of SO and group is nothing but the symmetric group, the two-dimensional symmetric group, and this group gives us the curvature. Okay, so we can say that the holonomic algebra is a subgroup of the curvature tensor algebra, and the holonomic algebra is named by the holonomic algebra. Of MG. So here the crucial question, this question is like this: why the holonomy is important for us? The reason is this: why it's important. Why? Is the holonomy of MG important? The reason is this: actually, holonomy is directly interrelated with the curvature. Okay. So the curvature gives us the idea, gives us the information about the geometry, and that's why curvature is important, and the holonomy is as much as important with the curvature. And another information, so the holonomy is interrelated to parallel tensor fields. And we know that the parallel tensor field is very important for the geometric and the physical object. Somehow you have to preserve the tensor field, and at least you have to preserve the parallel condition. And the holonomy is directly related. And another importance of the holonomy is compatible with the extra geometric object, geometric structure. Geometric structure. For instance, the Kähler condition, being the Kähler is the geometric condition, so you have to check that which geometry preserves this condition. So the holonomy group, if your holonomy group is fixed, you can say that somehow the Kähler condition preserved, or the spin structure, also the geometric structure, and you have to you have to think about that in which condition preserve this spin structure. That's why the holonomy is an important concept. And also this structure we will define it later. If you know that structural group, if you know that the vector bundle of your manifold, and you can say that the holonomy preserve geometry, preserving these geometric structure. Okay, that's why we focus on holonomy. And let's see what's the relation with the curvature. Let's again, we will start with the tangent space Txm. Okay, so the remaining curvature tensor maybe we can write like this Rm G, and it's an element of T, the dual of tangent space, tensor it 4 times. Okay, this is the general space for the Riemannian curvature tensor. But we know that the calculation is so complicated for the Riemannian curvature tensor that we have various symmetries. Symmetries, for instance, which kind of symmetries? Ij, Gl is minus R, J, I, Kl. Now the first two components, or you can switch the blockwise change its combine plus is equal to plus or minus, and just a sign change for these symmetries, and the remaining curvature tensor vector x. We can say that this is the element of the symmetric tensor. T star, and we know that this is the dual of T for A. And the fact actually we can take special importance the holonomy algebra constrains the curvature. Okay, so because we know that the Riemannian curvature tensor is also or before, but here of and symmetric. Okay, and this is very famous theorem that the proof is you can check from George book or other differential geometry book related with some holonomy. This theorem is named by Rossi-Singer theorem. The theorem says that the holonomy algebra is generated by actually generated by the curvature. Okay, so the holonomy algebra X is the subgroup of holonomy algebra of SON is the subspace N by what? By this element P gamma inverse of R X y with respect to y of P gamma. So our gamma is an add for X to Y, and X and the bigger X and Y is element of tangent plane. We can write here X, Y, T, X, T, Y, M, okay? And let's sum we have our X, Y to Y is element of the holonomy algebra of M is the remaining curvature. Is the curvature and the morphism. Okay, so this theorem is the famous theorem about this theory, and we can say that the holonomy algebra is actually generated by the curvature, and they are directly interrelated to each other. So we guarantee that now holonomy is generated by the curvature, the remaining curvature, and we have two different important issue about the holonomy. One of them is we have to mention about the parallel tensors, and we will give some classification of holonomy, and finally we will cover the share classification. How do we classify the holonomy? So just we can cover. So we say that the holonomy is spanned by the remaining curvature. This is our packet. Now we try to understand the parallel tensor field, and after that we will continue the geometric structure, how do we interrelate to each other. Finally, we will classify the holonomy, which kind of geometry, which kind of holonomy, and Berger classified that the holonomy spaces. And after that classification, we will maybe finish. Just I have to say something a little bit faster. The holonomy representation. The holonomy representation determines which tensor fields as of actually, if your tensor field is parallel, we can say that your the derivative for the whole direction has to be equal to 0, and the whole principle let x element of n. So we can say that if S parallel tensor field, then this tensor field at the standard point between x fixed by the holonomy action So, I said before, the holonomy just measure the angles or the rotation actually, but it's one-to-one correspondence between the GL TXM. So this is the matrix element, and this matrix element fix you the parallel tensor field. Okay? And if SCO fixed, this is not so okay, not confused. This is S sub 0. G action on TXM, then there is a unique parallel tensor field S with S to X equal to S0. So the relation between parallel tensors and holonomy is this one. I mean, holonomy representation. If you choose a parallel tensor field, holonomy, and this parallel tensor field fits fixed by your holonomy action, and if you choose a fixed X0 and this our holonomy action gives us a unique parallel tensor field as well, other tensor field. And the last part, the relation with the extra geometric structure. How do we write? This is the parallel tensor field part, the third part, the extra geometric structure. Let's n G Riemann manifolds. Riemann M manifolds. Okay. And here is the following. Let G is the group of or n, okay, of the one group. The followings are equal. Followings are equal. So the first one is that holonomy G is the subgroup of G, okay? So we can say that there exists a G structure. This structure on M that is G compatible of torsion free. Okay, so we didn't say anything about that, the G compatible, torsion free, and G structure. It is the at the beginning of the differential geometry course, or maybe graduate level, but we can say something about that by using some example. Okay, what's the meaning of the G structure? Again, the non-trivial example here, if you think about that two-dimensional manifolds, sorry, even-dimensional manifolds or two-dimensional, two is more or less, and even, okay, so consider our G is that this is the sum of for n, okay, and here that torsion free n over 2 structure is just a scalar structure. Okay, so and the previous G and G, where G is the G parallel geometry complex structures. Okay, and therefore we can say that the holonomy G sits in U n over 2, okay, and G is the scalar matrix. So from here, the G is related with the structural group if you put an extra structure for here your spaces. Okay? The structural group means that if you remember the definition from the manifolds, if you choose a two open set, if you look at the intersection, okay, for that intersection, the atlas of your manifold, or if you have the phi n, this phi n sends to from each open sets to Rn, and the intersection or the overlap point, you can find another map, and that map is element of GLM, and it's if it's equal to specific group, it's the structure group of n. And if you choose that G is UN over 2 and even dimensional manifold, torsion free means actually geometrical, there's no shift. Your geometry shift at this point is like you have the fixed coordinate basis, but if your coordinate shift a little bit for each point to point, this is the torsion. If you twist your spaces, but in general we are focusing on the torsion-free spaces, and Mn is torsion-free. And for this structure, you end with the two structure is the Taylor structure. This is the geometric structure, and J is the almost complete structure. This is also defined with a tensor, and for this tensor. if your holonomy is actually the geometric object, your n over 2, we can say that your metric is the Kähler metric, okay? And somehow we can say that the holonomy is preserved the geometric object, geometric information. Okay. The last thing, the classification. Holonomy. Classification. Okay. So at first, we will think about the products. So if G is if your metric is the product metric G1, G2, so the direct result, then you can define the holonomy G is nothing but the holonomy G1 equals to holonomy G2. Okay, if your metric is a product, directly our result is holonomy 2. And definition here, let's N G Riemannian. So here he is globally reducible. If G equal to G1 plus G2, okay. If you can separate your metric into two pieces, okay, the direct product of the two spaces, we can say that G is globally reducible. And the second one is locally reducible. If any point in N has globally reducible neighborhood. So, you know, I mean, there are two different definitions. The globally reducible, so we can say that directly the locally reducible, but the reverse is not always true. And so G is irreducible. G is irreducible means and G is not locally reducible. Okay. So there's no permission for reducible case, and we can give just last and locally symmetric last thing maybe. So I want to definition locally symmetric if the remaining curvature has a 0 and some is this one. We want to classify holonomy if G is locally reducible of G locally symmetric, then we can understand the following G object. So other cases, if not a reducible, irreducible, we can reduce into irreducible pieces. Okay, that's why, and I want to understand that the core of holonomy actually, and we can understand the rest parts. The final result of this theory, how do we classify the holonomy? This is the final result when we have classified everything. So let M and G simply connected. At the beginning, we say that if your space is simply connected, we can say that the reduced holonomy and holonomy are equal to itself, and assume the not locally reducible. So we cannot reduce, we cannot separate, not locally symmetric, and holonomy G is one, and we have to do a table for the Berger classification. If holonomy is, again, I mentioned that holonomy is simply connected, and this simply connected means holonomy, reduced holonomy and holonomy are equal to itself, and we know that the holonomy is subgroup of SON. So if your holonomy, and we can say something about the dimension and some special name for this manifold. And in some cases, we know that the curvature, or roughly we can say something. Okay. And here, the holonomy of SON, the largest group, somehow we know that the holonomy is subgroup of SON, so the dimension can be anything, okay? And for that manifold, just orientable manifold, there's no other information, and the curvature can be anything. But if you choose a specific geometry, I gave an example. So this n is equal to 2m. This means that even dimensional object and the name is Taylor manifold. And for the Taylor manifold, there's no specific character. But if you choose SU equal to 2, okay, so if you choose the orientable one and special unitary group, again, n equal to 2m, and the even dimension. Now we forced our K-liberty condition with the special unitary group, and this name is Calabi-Yau manifold, and we're famous for the last 20 years maybe. And the curvature of Calabi-Yau manifold is H of X, and that's why I mean is very useful for the physical information, the H of X, and SP 4, and this is the actually 4m dimensional object. The dimension has to be divisible by 4, the hypercase. This space is also OH flat, very interesting spaces. And over 4, 1, again 4m, the quaternion Taylor. This is Einstein. And G2 n equal to 7, and this is named by the G2 and also H of it. And the last one, spin 7, n equal to 8. Okay, and the spin 7 manifold and also H of it. And finally, spin 9. The Gaussian classified the spin 9 and the dimensional 6. Spin 9, dimension 16. But the brown and gray prove that the last part, brown and gray, prove that the holonomy spin 7 is symmetric. Spin 7, so spin 9 is symmetric. So this is all of our list, and you can take it out. Okay. So the famous list, if you here UN is a scalar over 2. If you fix your determinant, actually you will find the Calabi-Yau, the hypercalar, and if you fix your if you fix your determinant, you will find another spaces, and also for G2 and spin 7 interrelated to each other. Also, if you are living in spin 7, if you fix your the determinant, it's equal to 1, and then you will find the G2. Okay, so these two spaces are interrelated to each other. These two spaces are interrelated to each other, and also G2 and spin 7 interrelated to each other. This is the 4-dimensional object, 2-dimensional object, and 8 and 7-dimensional object. Somehow we will cover these spin 7, but more or less lots of information induced from G2 or the vice versa. And the same thing here, the Kähler and the Calabi-Yau condition is the same idea, but we will cover the spin 7 using the information from Taylor and the color yellow information and some part of the G2. Okay, and now we have to measure spin 7 manifold, and maybe tomorrow we will talk about the long space and the long algebra, and later we will continue with the, if we are living in an 8-dimensional object, we have to talk about octanions. So we have to talk about spatial geometry, multiplication, measure something, and at the end of the lecture, we will understand the spatial geometry and some part of the mirror duality. Okay, that's enough for me. If you have any question, you can ask. Otherwise, Mustafa.
Any questions? All right, thank you very much.
Can I ask something?
Sure, yeah, go ahead.
So we, in defining the holonomic group, we used P gammas and gamma was a loop. So how do we construct P gammas from a given gamma, a loop? So P gamma was a general linear map, linear endomorphism on the tangent space at X to our manifold M.
The P gamma is just a parallel translation. Parallel translation element is if at first you have to choose in a loop. Okay, for this loop you have to pick any element from your tangent space. Where for each point you can define the tangent space, and if you pick any vector for that tangent space, actually you have to slide a little bit, and you can find the transformation group, right? For each two different vectors, if you pass along with your gamma, you have to define a matrix element, and that's a matrix element actually has to be element of the parallel translation. Parallel translation means if you are you have to preserve this is our element for a vector, not a two-dimensional. We have more dimension. This is our vector. So you have to preserve this angle. If you change here, again, you have dimensional derivative, okay, the derivative of this gamma, and you have to preserve this theta also. Now, this transformation, okay, this transformation map define the matrix. So this matrix is element of GL, GLR, okay, and the matrix element actually. Does it make sense?
So we parallel transport the vector along the loop, but I don't see why this map has to be linear. And we don't really refer to the connection or the principal G bundles. Or,
and also we have another question from chat. Here, actually, for the Portman asked that, what if the algebra or the space was the form of direct sum of two different spaces lying in this table? Here, this table is the irreducible classification. If we have two different spaces, so we can separate. We can write that here. The product information, if you look at that, the classification start with, at first we have to take it out, reducible part. The reducible and the combination is the same as at the beginning. If your space is the combination of two different metric and the product of two different metric, you can define the holonomy with respect to two different holonomy. Okay, the cross product of two different holonomy. The same idea. If your spaces is the combination of two different holonomy, you can write that the irreducible parts and the multiplication or the product of the holonomy group. Okay, and so I mean you can define that these two spaces, but if your space is reducible, you can find the irreducible pieces. And the Berger list guaranteed that your spaces somehow has to be each piece is one of them the form one of these spaces. Okay, but I mean the irreducible part is the important piece. Otherwise, I mean, somehow, if your spaces is the Kähler time, the Kähler spaces, and also another spaces n. Okay, this is directly separated to itself, and the holonomy form here and holonomy form here. Just take. Directly shot G2 and spin 7 and independent from each other. So this space is not helpful for us about the geometry. So again, we have to holonomy G2, how about spin 7? So directly you have to, if your space is reducible, at first you have to reduce your space into irreducible pieces. You know, you maybe remember from the algebra exactly the same procedure. You have to separate the irreducible pieces. After that, you should understand the irreducible component. And the idea is exactly the same. If your space is the combination of these two holonomy, you have to separate at first, and you have to understand each pieces. Is there a question? No. Okay.
Okay. So thank you very much, Eyüp.